Hi, my name is Joe Chase, and I'm your instructor for Physics 2, asynchronously online for CCV during the summer of 2025. So I just wanted to say hi, and so you have an idea about what your instructor actually looks like. And I would like to take a look at a problem that a student had a question about. Now, you can do this too. If there's anything that you would like further details about, just let me know, and I will post a short video talking about that problem. The problem that was raised is actually a tricky one because um, student asked for the fifth assignment, the fifth problem in this assignment set, and it looks like this. Uh, yeah, there we go. Okay, so we have two charges, minus q and minus 3q, that are distance L apart. And normally they would repel each other and run away. But if we place a third charge, we could actually hold them in place. So how big would that third charge have to be, and where would it be located? Okay, I'm going to stop sharing my screen and pause while I set up my document camera. Let's get a sketch going so we can have an idea about what this would look like. So I'm going to reserve a location here for minus q. And then at some distance over here, we'll do minus 3q. And we're separated by a distance L. Oops, this should probably go all the way out here. There we go. Okay, so these two charges want to repel each other. And our task is to find how we can hold them together by using a third charge. So what's the nature of that charge going to be? Well, if it's negative, there's no place to put a negative charge. It's all going to want to just repel each other. So it can be a negative charge. So it must be positive. And if it's a positive charge out here, it's going to attract this one and attract this one. Both forces would be to the left. So that those can't cancel each other out. And same thing is true over here. So that means our Q3 has to be positive, and it has to be located somewhere along the line between these two. And we'll call that distance x. Okay, now we have a mutual force in between them. That's repelling the two original charges. That's the one that we have to neutralize. Right, and the magnitude of that force, I'm going to zoom in here for a little bit so you can perhaps see a little bit better. Do some focusing. All right. So there's a force in between these two, and that force is equal to Coulomb constant. And then the magnitude of the two charges. Now, we've already talked about the relative importance of who's plus and who's minus. So we really don't need to carry that through when we're talking about these charges. So this is going to be charge 1, which is Q, and the second charge, which is 3Q, and the distance between them, which is L squared. Now, we can talk about the force in between these two. So obviously, the repulsive force from minus 3Q is going to want to push to the left, and then the attractive force of positive Q3 is going to want to pull to the right. So those have a chance of canceling each other out. So let's see what that looks like. So we're going to have the force between these two, which is going to be Coulomb constant times the first charge times the second charge over the distance squared. And that has to be equal to the mutual force in between them. So that's going to be KQ times 3Q over L squared. Okay, so that's one of our conditions. Now we have two unknowns here. So one of the unknowns is X, the other unknown is Q3. And so we need a second equation if we're going to make this work. And the second equation is to do the same thing. We take the attractive force between 3Q and Q3 and set that equal to the original force. So that attractive force is going to be K 3Q times Q3 over, and now the distance from here to here is not a third variable. It's related to X, but it's actually L minus X. Okay, and we set that equal to the original force of repulsion between the two. So K, Q, 3Q over L squared. And we'll put a box around that. So here are two equations that we can use to find the two unknowns, which are Q3 and X. Let's take a look. There's quite a bit of cancellation that can happen here. So the K's cancel out here and the Q's cancel out. And then over here, again, the K's cancel out. And one of the Q's also cancels out. Now I can rewrite this actually. So here are our two unknowns. We can solve for Q3 in both equations, and then set those two equal to each other. So let's see what that would look like. Q3 on this side is going to be equal to three Q X squared over L squared. And so I'm just going to kind of ghost write this here. I'll just write it very faintly. I'll use a pencil here so I can erase it later. So this is saying that Q3 equals. And now over here, same thing, I'll try and get Q3 all by itself. So I do that by multiplying both sides by L minus X squared. And so now I'm going to have 3Q times L minus X squared over L squared. And again, I'll kind of write this lightly in pencil equals Q3. So that means that these two have to be equal to each other. And so I can just kind of erase this now. Because let's take a look at algebraically what's going to happen. L squareds cancel. Okay, great. And the Q cancels, right? That's what happens when you set these things equal. So now we have a relationship that's just about the relationship between L and X. And so we have a chance at solving that. So that means I've got 3x squared. Sorry, I could have canceled the 3 also, right? Well, I'll just do that here. Just double check that, make sure that's right. No, it's not right because there was a factor of 3 here, a factor of 3 here that canceled. Okay, good. No, it's not there. Okay, so now we have 3x squared equals L minus x squared. Okay, so we're pretty close. We were trying to solve for x in terms of L. All right, now when I looked at the solution to this, I realized that sometimes, not sometimes, all the time, that textbooks will hire graduate students to do solutions to problems. And in this case, the graduate student made a mistake, and I'll show you what the mistake is. The mistake is to come in and do this, to say, okay, we can just take the square root of both sides. And so I have rad 3x is equal to L minus x, and now I can solve for that. So if I add a factor of x over to the other side, then you can see that I have x times rad 3 plus 1 equals L. And then x is going to be equal to L over rad 3 plus 1. And that's the answer that's, whoops, sorry, got a little there. That's the answer that's shown. So now I could take this, if I know what x is, and I can stick this into one of these equations over here. Then I can figure out what Q3 is going to be. So I'm going to take this, drop it down here, and that is going to be Q3 over x squared is equal to 3q over L squared. So now I know what x squared is. And it's equal to L divided by the square root of 3 plus 1. So Q3 over, and that's going to be squared. So that's L squared over the quantity rad 3 plus 1, which is actually just a number. I mean, I could have calculated what that number is equal to 3q over L squared. And you can see that the L squareds cancel. And then I can multiply both sides by 1 over rad 3 plus 1 and get a value for Q3. So Q3 is now equal to 3q over, and life is still squared here. So rad 3 plus 1 squared. All right. And then those are the answers that are given. But here's the issue. This is wrong. Why is it wrong? Because when you take the square root of both sides, really both plus and minus are possibilities. So they just kind of discarded the minus as being one of the possibilities. And so here, really what the proper thing to do is to expand out this binomial. So this would be x squared minus 2xl plus x squared, and then try and solve for x in terms of L that way. So that's what I did the first time I did this problem, and I saw the wild divergence with the answer that was in the bug. So this is what they were looking for. This is how to get it, but this is actually a mistake. All right, I hope that helps.